A battery of EMF 12 volts and negligible internal resistance is connected to a resistor of constant resistance 6 ohms, an ideal ammeter and an ideal voltmeter. Okay, what is the reading on the ammeter and the voltmeter? The first thing is that you should know enough about circuits to recognize that something's wrong there. A voltmeter has really, really high resistance, so if you plug it in series with stuff, it's going to stop the current. So, the ammeter reading is going to be 0, so it's either this one or this one, C or D. The voltmeter reading, well, the voltmeter is actually connected to the two different sides of the battery. It's connected to this side of the battery and to this side of the battery. Those two, so this side is actually connected into that pole of the voltmeter, and this side is connected into that pole of the voltmeter. So it's going to measure the battery voltage. So it's going to measure 12 volts. Okay, so D is the answer. Four kilograms of water at 100 degrees Celsius is mixed with 1 kilogram of water at 0 degrees Celsius in a container insulated from the surroundings. What's the final temperature of the water? Okay, so here we can go Q lost equals Q gained. And so we have MC delta T on this side. How much did we have? 4 times C times final minus initial TF minus 100. That must be equal to the negative of, how much do we have? 1 kilogram. 1 times C times final minus initial TF minus 0. Okay, and then we can cancel the C's because they're on both sides. And so what we end up with is 4TF minus 400 on this side and negative TF on this side, which means we end up with negative 5TF is 100, so it's going to end up at 20 degrees. Or is it? That's not quite right. Oh no, let's just double check that. I think I skipped a few too many steps there. Let's just write up the last step here. So we have 4TF minus 400 is equal to negative TF. And so we end up with negative 5TF is equal to negative 400, sorry, which means we're going to end up not with 20, but with 80. Okay. Number 13. A string is made to vibrate at its third harmonic. There we go. Which of the following compares the period of vibration of P and Q and the average speed of P and Q? Okay, so P as a they both have the same period because they're both on the same string. Every time this one vibrates up and down, this point's going to, every time P vibrates up and down, Q is going to vibrate up and down at the same time. And so the period must be the same. The average speed, in that time, P will travel a shorter distance than Q. So the average speed is a scalar, remember? So it's not average velocity. If it were average velocity, they would both be 0. But we're talking average speed here, which is just the magnitude of the velocity. And so the average speed is going to be different. And so B is the answer. Okay, because P travels a shorter distance in the same time as Q, so P is going to have a smaller average speed. Which of the following is the temperature of an object related to? Kinetic energy of the object? Nope. The random kinetic energy of the particles in the object. That sounds pretty much like the definition that we learned. It's not related to the potential energy, and it's not the sum of those two, because that's the internal energy. The potential energy doesn't influence the temperature. The acceleration of an object executing simple harmonic motion is proportional to the displacement of the object from equilibrium. Acceleration should be proportional to the displacement. That's the definition of simple harmonic motion. Okay. 16. Which of the following is a statement of Ohm's law? The resistance of a conductor is constant. The current in a conductor is inversely proportional to the potential difference across the conductor, provided the temperature is constant. So let's just see. Ohm's law, V is equal to IR, and it's only true if the temperature remains constant. And so I is equal to V over R. So the current is inversely proportional to the potential difference. That's not true. The resistance of a conductor is constant, provided that the temperature is constant. The current in a conductor is proportional to the potential difference across it. This is not Ohm's law. It's C or D. The resistance of a conductor is constant, provided the temperature is constant. That's true for all ohmic resistors, so that's the most likely one. This is not always true, so this is the answer. C. (17) Three identical filament lamps, W, X, and Y, are connected to the circuit as shown. The cell has negligible internal resistance. When the switch is closed, the lamp's light, which describes the brightness of lamps W and lamp Y. When the switch is opened. Okay, so when we close it, all the current goes through W and only some of the current goes through X and Y, which means that W will be the brightest. When we open it, the voltage gets evenly split between W and Y because they're identical. Therefore, W will get dimmer and Y will get brighter. So W will get dimmer, which is either A or C, and Y will get brighter. There we go. Because Y will get more current than it used to, and W will get less current than it used to. Okay. 18. 4-point charges of equal magnitude, each fixed to a corner of a square. W is a positive charge, X is a negative charge. The arrow shows the direction of the resultant electric field. What are the correct signs of charge Y and Z? So W is positive, Y is negative. Okay, so we want an overall field towards Y. So Y is going to be negative. No, it's not. Yeah, Y is going to be negative and Z is going to be negative. That's the only way to get an overall field, because that means that these ones, this cancels out that, and that adds to that, which means that we get an overall field towards Y, which is what we want. And so the only situation where we have Z and Y as negative is D, so D is the answer. 19. The diagram shows the fundamental first harmonic of a standing sound wave in a pipe, blah, blah, blah. At any instant, all of the molecules of air in the pipe oscillate with the same phase, amplitude. We know it's not amplitude. They definitely don't oscillate with the same velocity. And it's either phase or acceleration. In this case, because it's the first harmonic, they're all going to have the same phase. That's because if one of them is up, then all of them are up. If one of them is down, then all of them are down in terms of this transverse representation. Or if one of them is heading towards the closed end, then all of the molecules are vibrating towards the closed end. They just vibrate back and forth. So here we have them vibrating back and forth like this. And here they're vibrating back and forth exactly in phase, but with a smaller amplitude. Okay. 2-point charges of size +2 and -q are placed as, or +2q are placed as shown. In which of the regions 1, 2, and 3 can the resultant electric field strength be 0? Okay, so it's being attracted to the negative. So if you imagine a little test positive charge, it's got to experience the same force due to both. It's got to be further away from the stronger charge and closer to the negative one. So it's got to be in zone 3. That's the only place where it can experience 0 electric field.